Imagine the CPU on your database server has been trending upward for months, but your monitoring tool sees a flat line. Well, you have a problem. And this is what happens when you apply a fixed average to dynamic data. And this is a pretty common and costly mistake. In this video, I'm going to try to show you how to fix this blind spot and transform your team from reactive firefighters into proactive operators. The core issue here is that a standard moving average assumes the future always looks like the past. And when data has a clear upward trend, a fixed average is always going to be lagging behind. And this is going to create a monitoring gap. Your alerts are never going to be triggering at the right time, and you're not going to be aware of the issue until you have a full-blown incident on your hands. Now, to fix this, we're going to be looking at two different approaches. First one is called signal decomposition. And here, it's really interesting. We're going to be able to separate trends and seasonal cycles, and what's going to be left over is the true anomalies we want to keep our eye on. The second one is called an exponentially weighted moving average, or EWMA, and this just gives more weight to recent data. Both methods ensure that we're going to be monitoring today's systems and not last quarter's. So let's look at that first option, option A, signal decomposition. We're going to be referring to our CPU utilization as our signal. This is the signal that we're interested in monitoring and alerting on. Now, what we're saying here with y equals t plus s plus r is that our signal, our CPU utilization, is actually made up of different components, right? It's made up of three components. Two of those components, t and s, represent respectively the trend, the baseline trend of CPU utilization for that week, and the morning spike. Because it's a Monday morning, it's 9 a.m., we expect that there's going to be a spike in utilization. So those observations we don't really want to pay too much attention to. What we really want to keep our eye on is whatever is left over. It's that R, that remainder. That's what's going to be worth alerting on and monitoring. So how do we go about obtaining these values? Well, number one, you're going to obtain T, right? And what you're going to do is that you're going to be averaging out your hourly data, all those observations, all those values of Y that you've collected, average those out per week, right? And that's going to smooth out your daily peak. So you're going to be eliminating outliers and have a better representation of the behavior of the CPU utilization. Once you have that, you're going to want to obtain S, which is what represents that spike. And so the way to do that is, for every hour that you have a CPU utilization for, you're going to subtract that T that you obtained in the previous step, right? And that's going to give you a set of numbers, right, of Y minus T's, Y minus T, Y minus T for every hour observation that you have, and you're going to average all of those out. And now you have that spike, right? You're going to have the value that represents that spike. And then the final step is obviously calculate R. And to calculate R, you just solve for R in the equation, which means you take Y and you subtract T and S. So for every raw value of Y, you're going to subtract T and S, right? So you're subtracting the predictable trend, right, and the seasonal spike from the raw data. And the remaining value represents true actionable noise, right? That is exactly what we should be setting your alert thresholds on, what we need to be keeping an eye on when we're monitoring. So let's look at option B. The second approach we call the exponentially weighted moving average, and it's represented there by that formula. Let's not go into try to overcomplicate things. It's essentially a weighted average, right? That's what's the name is. You're giving a weight to the current data observation, which is represented by x sub t, and you're giving another weight to the moving average you calculated at the previous time, right? So the moving average at time t, at the current time, right now, depends on the moving average at the previous time, right? And everything really depends on the value of alpha that we choose. So by adjusting that alpha value, we control how quickly the model adapts, right? And so a higher alpha means the model leans heavily more towards a recent data point, while a lower alpha means that it's using more historical data and it's providing a smoother, slower response. So let's look at the business impact of adopting these approaches that we just discussed, right? What is it that we bring to the business? And that's the important part of the conversation. So number one, we started the whole conversation saying that fixed averages don't really help us out. They don't really represent the reality across time, right, over time. So we're going to be more accurate by using dynamic thresholds, right? But it's not just about accuracy. Working with dynamic thresholds is also a means to help us deal with alert fatigue, right? That the phenomenon that happens when our monitoring teams are being constantly hit by tons of alerts, and it's difficult to differentiate between the noise and the actual signal, and we don't know what to react to, and we miss the important alerts because we're paying attention to other things, right? This is a really important tool to deal with that, because by eliminating constant false alarms from predictable workload peaks, our engineers are going to be able to regain the trust that they should have in their dashboards and what they're seeing, because only true anomalies are going to be triggering alerts, and the team is going to be able to respond much faster and much more effectively. Second business impact. Static averages, they're the only fire where the system is already broken, right? And we're missing those early signs, like those gradual memory leaks and other things that impact performance. So by shifting to this predictive decomposition, we can catch those deviations before the damage is done, right? And this brings out another business impact, which is protecting our customers' experience, our revenue, our brand reputation, because we're going to be able to intervene earlier. Detect the real problem, react to it, determine what needs to be done, and resolve it even before it becomes an incident. And finally, this approach benefits the business also by improving capacity planning, right? So, simple averages, they lead to either performance bottlenecks or expensive, panic-driven over-purchasing or over-provisioning, right? And that's what we tend to see. So if we do good advanced forecasting and we use things like machine learning baselines, and we provide more accurate demand predictions, and that's going to allow us to maximize utilization and eliminate those wasteful, cloud expenditures, and minimize costs and optimize the use of our resources. So what's our takeaway here? Simple, right? Fixed averages keep us looking backwards. We need to shift to dynamic, context-aware monitoring, and that's going to be the key to reducing downtime and reducing costs. So this is what's going to allow us to adopt predictive operations and turn IT into a true business driver and not just a cost center. If you found this useful, if you found this information of value, please let me know. If the approaches interest you, if there's more detail that you would like to see, I would love to hear from you. I would love to also know how your team manages thresholds and monitoring and alert fatigue. Thanks for watching. My name is Pavel Warisma. If you'd like to discuss how to apply these strategies to your own environment, you can always reach me through LinkedIn or visit my website at itoutcomes.ca or send me an email. We can work together and we can turn your data into better decisions.